Alright, so the next part of linear systems is matrices. So this is just the introduction to matrices. We have used matrices before in the previous examples. Let me just draw one up right here. You know, oh shoot. Oh shoot, I accidentally unplugged my... Anyways, it's something like that, and we've used it before. Like for example, this is one of like the past examples, showing reduced row echelon form or something. But those are all matrices used in the context of, showing linear systems, right? But matrices can be used to represent whatever, right? So it's kind of a bit more of a vague thing. When we use a matrix like I was used before in the form of like to represent linear systems where you have this and then you have that line and everything beyond that line is just like what it equals to, that's called an augmented matrix. But for regular matrices, there's a few things to keep in mind, which is just a bunch of like basic stuff. There's more to delve into with matrices, but it's basically things like notation. Every matrix has an order, and its order is like m times n, right? It's a bit of a confusing way to do it because let me try write this backwards so it's easy to see. It's a bit of a weird way to put it. Can you see that? Oh yeah, that m times n, right? The way to do it, because you don't actually multiply the numbers together, so you can have like 3x2, something like that, and that isn't 3 times 2 equals to 6. That represents 3 rows and 2 columns, because the m represents rows and the n represents columns. And that represents the rows and columns in a matrix. So usually you use capital letters to denote a matrix. So it's weird to write this backwards, right? So you can say like A is a matrix that has a order of 2 by 2, which means it's a 2 by 2 matrix. Like that, it can have like whatever number in there, but 0 is easy to write because you can look at it forward, like you can flip it around and it'll look the same. But yeah, that's generally like how you denote the size of a matrix. And there's another way to denote the elements of a matrix, where you would have, like, let's say the matrix is capital A, then each element will be represented with a lowercase a, right? So inside that matrix, it's just a bunch of lowercase a's. And then each of those will have a number, right? So the first one will be A11, and then the second A will increment every time you move to a different column, and the first A will increment every time you move to a different row, right? So if I go down, it's A21, right? So it's A11, go down, it's A21. But if I go to the right, it's A11, then it's A12. If I go to the right and down, it's from A11 to A22. So okay, can I just click flip? No, I can't. What the heck? Well, that's backwards, but you can kind of get it. You kind of get what it means. Oh, if I do O, yes. So O is a matrix. Let's do something a bit bigger. So let's have a bunch of lowercase o's. 1, 2, 3, 4, 5, 6. All right, and it'll start with a 1, 1. Down, that's a 2, 1. Shoot, this is not that nice writing it backwards, I will say. So it'll be something like that. So O is a matrix and it has O12, O11, O12, O13, and that is the way we put it is OIJ. Did I do that J? No, that J is backwards. But it's OIJ, and I represents the row and J represents the column, in the same way that like M and N represents row and column. There it is. So the first one always represents row, the second one always represents column. And you know, there's a few ways to represent it. So I mean that's how you represent the array, but then I mean the matrix, but you put it in brackets, and then after that you put in the ij. This represents the element in it, so that's like aij equals to like the element aij. If you do a23, then it's whatever number you have in that slot in your matrix. But I keep mixing up matrix and array, I'm sorry. But yeah, so basically through what's really explained here is you know, just addition, subtraction, basic things in matrices. Oh, one thing to note is that if the matrix has either one column or one row, then it can also be you can also call it a vector, and vectors have special ways of being represented. So you wouldn't do just like a capital letter. You would sometimes do something in bold or like with a squiggly line underneath that's very small. But yeah, so since this is just the basics, there's stuff I don't really need to go into. You should know this already. Yeah, is it here? The heck am I? This 5? What did... There's one more sheet. Oh, it's here. Yeah, also if a matrix has a row, the row and column the same, it's a square matrix. Pretty self-explanatory. But yeah, you can just do addition and subtraction normally. You just add and subtract the corresponding elements. You can only add and subtract if both matrices have the same order. That's something to keep in mind. If you multiplying by a constant is easy. So if you have a matrix A, capital A, bunch of random numbers inside, you multiply it by 5. You just multiply everything inside by 5. That's very simple. It is a bit more complicated if you multiply two matrices together. There's a whole process behind it, but basically, A has M and N, right? A has a row and column, B has a row and column. If you multiply it to get matrix AB, the column of A and the row of B has to match. And the new matrix AB will take the row of A and the column of B. And there's a very simple way to explain this, which basically involves... It involves something like this. So you have A to the power of, let's say, 2 by 3, and then B to the order of 4 and 5. Now, since you need the row of A and the column of A, the row of B, the column of B, the column of A and the row of B have to match. So here, 3 does not equal to 4, so that doesn't match, so you can't do this. But if, let's say, A has order 2 and 3, B has the order 3 and 5, these two match, right? Which means that it is valid, and the new array, the new matrix AB will take the row of A and the column of B, so it will be order 2 by 5. So that's a really simple way of doing it. So here you just cancel it together and then you smush it together, it's AB. So now you have this thing that's 2 rows, so that's AB11, AB21, and then you go all the way to AB15, AB25, and so this is your new array. But how do you actually get this, right? How do you find the value that that's supposed to be? Well, you can go to the values of A and B, and basically there's this, I wrote it down here, it's pretty well, I think, where let's say A is this matrix and B is this matrix. So you have A1, 1, 1, 1, 2, 2, 1, 2, 2, 3, 1, 3, 2, same thing here. To get value, the combined value A, B, I, J, right? You want to find the sum of the products of the corresponding values of row I in A and column J in B. That sounds a bit complicated, but it's actually pretty simple, right? So here, I is 3, right? Because I is 3, j is 2. So since I is 3, you want to go to row 3 of A. This is row 3 of A. And since j is 2, you want to go to column 2 of B. So this is column 2. And you take those and you add it together. So this is equal to this A31 multiplied by B12 plus A32 multiplied by B22. So that's a very simple way of looking at it, right? So this is 3, 2. Then you go here. Okay, so this is 1, 2, 3, third row. 1, 2. This is the second. So these two multiply plus these two multiply. And it works for like any big matrix, but that's generally how that multiplication goes. Other than that, you can like partition a matrix. So this is a matrix of matrices where you're just splitting this, and I think it helps with some stuff and it explains some stuff, but it's not really. It's good to keep in mind, right? This is good to keep in mind, because you know, if you just want to find this specific column of AB, like AB here, you only want to find this first column. Instead of multiplying everything, you can just be like, okay, let me just partition A and find like this part of it, right? And you can say like, okay, so the to find the jth column of AB, let's say like, oh yeah, I wanted to find column 1, then that's just A multiplied by the first column of B, right? So you can multiply this by just this one column. You know, it simplifies things quite a bit. That's that. Next part is this. You know, that's the same thing where you can kind of like split things together. You can just tie these things up. Let's say, you know, you have this big thing. This is what I was talking about a bit earlier with this links to, you know, the whole like augmented matrix thing and linear systems, where you have all this like random stuff and you're like, oh, it's a matrix, but there's a bunch of random values. Oh, it equals to something. Bam, that's a sign. And then I was like, okay, so x1, x2, x3. Oh, okay, this is a pattern. All right, split it. Right, let's break it up, and then we can simplify that. I'm going through this quite quickly because I don't think it's the most important. And then the last part is it's again quite simple things. You can just transpose a matrix. That just means flipping it. That means like if you have a matrix here, let's make it a bit big, right? Let's do A, B, C, E, F, G, X, Y, Z. That's all the alphabet that exists. If you want to transpose it, you just kind of like flip it around. So these two swap, these two swap, these two swap. The middle stays the same. But that's basically, you know, A, E, X, B, F, Y, C, G, Z. Now you might be like, well, what the heck was that? But it's basically, you see this, it's like flipped, you know? So it's kind of like here, A, F, Z, and then there's A, F, Z, and then right? It's flipped. You flip it like that. You flip it like I have this paper, and then right down the middle, and then I flip it, you know? And this isn't only for square matrices. You can have something like this, A, B, C, D. And if you transpose it, it turns into this, you know, A, B, C, D. So everything just flips. That's very simple. A trace is just, okay, if you have a square, it's the sum of like the diagonal. The diagonal always goes like from the start, you know, from the top left, like the A11, A12, A22, it should. A11, A22, A33. Sorry, oh my god, I keep messing this up. But yeah, it's basically that. So yeah, pretty simple matrix. That's all. That's everything. That's everything. Yeah.